For the rest of the chapter, we're going to focus on groundwater, or water that's found underground. So groundwater exists in all of the pore spaces, or the tiny holes between different grains of sediment, as well as in the joints and the breaks inside of the rocks underneath. But we're going to see that groundwater is incredibly important because it's the largest reservoir of fresh water that's easily available to humans. We can't drink salt water, so we can't drink our oceans. We rely very heavily on groundwater to exist. So worldwide, about 44% of all of our water needs as humans comes from groundwater alone. And out of all the water that we're taking out of the ground, about 40% of it's used for agriculture to grow our food, and about 25% of it is used for industry needs. But we're going to see that groundwater is incredibly important, especially when it comes to us overusing groundwater. If we use too much groundwater, a lot of really negative things can happen, like decreasing the amount of water within our streams. The land can start subsiding or start sinking down, and it can lead to increased water costs. But in Florida, we also need to look at groundwater as a really important erosional agent. And that's because groundwater is very slightly acidic. And over time, it's going to be able to form things like sinkholes and caves inside of that rock called limestone, which makes up the majority of Florida. So naturally acidic water is going to eat through that mineral calcite that makes up the rock limestone, eventually forming these sinkholes and caves. All of the groundwater that's stored under the ground came from some form of rainfall. That rainfall was able to infiltrate into the ground, and again, the amount of infiltration is going to depend a lot, especially on the slopes, how steep is the gradient in the area, what kind of surface material covers it, how intense and how long did the rainfall happen, and if and what kind of vegetation is on the surface. We're going to see that at the very top of our soil, we're going to have what's called a belt of soil moisture. This is just going to be all the upper soil having a very thin film of water along them. But if we can look a lot deeper below this, we'll see what's called the zone of saturation. This is going to be an area of the ground where the water is going to be completely filled with, the ground will be completely filled with water. 100% of the pore spaces will be filled with water. And the very upper limit, or the top of the zone of saturation, we call the water table. And everything above the water table we call the unsaturated zone. This area will have some water inside of the sediments and rock, but because it's not 100% filled with water, it's unsaturated. If we look at the shape of our water table, we're going to see that it's irregular. It's not completely flat like a table is. But it's kind of like a copycat of the surface above it. But things like steep gradients and hills are going to be a lot more subdued in the surface of our water table. But if we see that the ground is moving downhill, the water table deep beneath the ground is also going to move downhill as well. But we're going to see that the water moving beneath the ground is going to flow just like a stream. It's always going to move in areas of higher elevation to lower elevation. But the actual height of our water table is going to be dependent on the amount of rainfall in the area recently. More rain means more water will have infiltrated, so the water table will be higher. If we're having the opposite happen, we're having a lack of rain during a drought, that water table will get lower under the ground. And we're also going to see that the permeability of our sediment, how easily the water can move through, is going to affect our water table as well. So they're going to be in two really important words when it comes to sediments and how much water they can hold and move through them. And the first of these is called porosity. And this is just overall the total percentage of pore space or holes within that sediment or rock. So these could be spaces between different individual grains of sediments. It could be joints or faults within a rock or a cave. And the porosity is going to determine the overall quantity or amount of water that can fit inside of sediment or rock. The higher the porosity, the more holes there are, the more water that material is going to be able to hold. But the second important term is called permeability. And this is the material's ability to actually move water through it. Just because a material might have a lot of holes, it does not mean that those holes are connected, which would allow a fluid to move through the material. We'll see that if the spaces between the sediment are too small, where the sediment's very compact, it'll be able to hold the water, but the water won't be able to move through the sediment. So we call this kind of layer an aquitard. It's going to be a layer of really fine clay sediment that's going to prevent water from flowing through it. But when we're looking for groundwater, what we want to look for is called an aquifer. This is going to be either a rock or sediment that has a really high permeability, meaning that the water is going to be able to move from space to space very easily, and therefore it's going to be easily withdrawn through a water pump. We'll see that groundwater is moving. It's just moving incredibly slowly because it's forced to move from one hole to another inside of that rock or sediment. And it's so slow that it typically only moves a few centimeters a day, less than an inch a day. But like I said earlier, groundwater is going to move from higher elevations of the water table to lower elevations because gravity is always pulling it closer to the center of the earth. But because we see that most of our streams and lakes are in our lowest elevations, we're going to see that most of our groundwater is moving towards a stream or a lake.